All right, so we've done this sort of a simple example of Lagrangian, but I thought it was worth doing a more complicated example that actually shows just how much easier the Lagrangian makes your life compared to doing forces. So the example that we'll do is one that you've seen before. So it's this block on a ramp example. Block has mass m, the ramp has moment of inertia I. I'm going to choose a coordinate system for this that's the standard one, so theta and r. And rather than writing F equals ma for this, we'll use a Lagrangian approach to kind of see how you do that for a system that involves multiple bodies, but also to illustrate that it actually opens a lot of doors for you that make life a whole lot easier. So if I'm using a Lagrangian approach, my first step is to figure out what the coordinates are. And so I've got r and theta, and correspondingly the time derivatives of those r dot and theta dot that I need as my sort of state variables for the system. Second step in the Lagrangian approach is to figure out what the Lagrangian actually is. It's the kinetic energy minus the potential energy. And the kinetic energy in this case actually is going to have two terms, right? So there'll be a translational kinetic energy for this block, right? This block I'm treating as a point mass. It's going to have some velocity and some translational kinetic energy, plus a rotational kinetic energy associated with the fact that this ramp can rotate back and forth or up and down. So I'll have a 1/2 I times omega squared, or in this case that will simply be theta dot squared. Okay? So that whole thing is what the kinetic energy of the system is, because the system includes both the ramp and the block, and I of course need to write that out in more detail with regard to what my variables are. So that v squared in particular is going to be a problem. That'll give me 1/2 m times, if I write my velocity here, my velocity is r dot times r hat plus r times theta dot in the theta hat direction. So my velocity squared will be r dot squared plus r squared theta dot squared, right? Because velocity squared would simply be this velocity dotted with itself. When I take it dotted with itself, I get r dot r hat dot r dot r hat, or r dot squared, and r squared theta dot squared from the dot product of this with itself. And of course, theta hat dot r hat is 0. So that will be my first term, and then my second term will simply be 1/2 I times theta dot squared. Okay? So that's my kinetic energy. My potential energy is actually pretty simple to write for this system. The ramp has no potential energy. The block's potential energy will simply have to do with how high it is, right? So my block's potential energy will be m times g times r times the sine of theta, right? So my total Lagrangian will be 1/2 mr dot 1/2 blah blah blah, right? The velocity, the kinetic energy of the block, kinetic energy of the ramp, minus mgr sine theta. Okay, so now what I need to do in order to find the equations of motion is start taking some derivatives and actually do the math. And I'll warn you, this is where you make mistakes with the Lagrangian approach, is it's easy to sort of be careless in doing the math. So one of my equations of motion will be the partial derivative of the Lagrangian with respect to r has to be equal to the time derivative of the partial derivative of the Lagrangian with respect to r dot. Okay, so partial derivative of the Lagrangian with respect to r, let's think about what that is. If I take the partial with respect to r of this, the first thing, partial of r dot with respect to r is 0. Partial of this thing with respect to r, I pull down a 2. It's 2 times r times theta dot squared. So I'm going to get an m times r times theta dot squared. That's going to be one term that will survive. This doesn't depend on r at all. And then this term does depend on r. Partial of this with respect to r is just mg sine theta. So the left-hand side of this is m times r times theta dot squared minus m times g times the sine of theta. Right? And then on the right-hand side, I'm going to take the time derivative of the partial Lagrangian with respect to r dot. Well, let's see. The only place r dot shows up here is right there. Right? There's no other r dots that show up, so I'm going to take d by dt of m times r dot. Right? And sorry, m times r dot, which is going to simply be m times r double dot. Okay? So at this point, I have one of my equations of motion, but let's do the other one as well. So the other one, I take the partial of the Lagrangian with respect to theta, right? And that has to be equal to the time derivative of the partial of the Lagrangian with respect to theta dot. Okay? And this one turns out to be a little bit more complex, so we're going to have to think about this one a little bit. So let's see. Left-hand side here gives me the partial with respect to theta. Well, this doesn't depend on theta. This doesn't depend on theta. The only theta here is right there. So the left-hand side, I'm going to get mg times r times cosine of theta, right? Still a negative sign. And on the right-hand side, I need to take the time derivative of the partial Lagrangian with respect to theta dot. Well, I actually have two things that depend on theta dot, so I get an m times r squared times theta dot plus an I times theta dot, right? But now, this is the thing I wanted to highlight here. When I take this time derivative, what depends on time in here? Well, mass doesn't depend on time, but r depends on time, theta dot depends on time, right? Moment of inertia does not depend on time. So I've actually got to use the product rule in here to do this. So I'm going to end up getting, when I take the time derivative here, I'll get 2 times m times r dot times theta dot, right? Plus m times r squared times theta double dot, right? Plus I times theta double dot, right? So this term actually gives me two terms, and one of them is a sort of chain rule term having to do with the fact that when I take the derivative of r squared with respect to time, I get 2r and then an r dot as well. Okay, so I've got a more complicated expression on the right-hand side here, but it's still not too bad. I can actually now figure out what my equations of motion are more neatly. So r double dot is equal to m times r times theta dot squared minus mg sine theta all divided by m, right? So I can cancel out all my m's, right? Notice that r double dot has this sort of centripetal term, and then also has a term that has to do with how much the ramp is tilting. On the other hand, if I actually figure out what theta double dot is, right? Theta double dot times mr squared plus I, right? So I'm collected this and collected this is equal to minus mgr cosine theta minus 2 mr times r dot times theta dot, right? So that's that term moved over here, and this term, right? Or in other words, theta double dot is equal to g times r times mgr times cosine theta minus 2m r times r dot times theta dot all divided by mr squared plus I. And if I try to interpret this a little bit, well, what do I have here? Here I have 2 times r dot times theta dot, right? This looks like the sort of Coriolis term that you get when you do the accelerations, right? When you do the acceleration in polar, you get that r dot theta dot kind of term. And notice that it depends on how far out you are, in the same way that this term depends on how far out you are, because you've now got in the bottom a moment of inertia. So you actually effectively have a sort of gravitational torque right here, right? mg cosine theta times r. And then you also have this sort of Coriolis torque right here, and that torque divided by the effective moment of inertia of the system tells you how fast theta is changing. So we have our two equations of motion now, and I propose that we have them with a whole lot less work than you would have had you actually gone through and done F equals ma with this.